The next objective that we'll see is describing how chromatography and mass spectroscopy can be used to detect presence of steroids in sports. So we have two techniques here. We're going to see these. Let's look at the principles of gas chromatography. So you're familiar with paper chromatography. So let's start here. So chromatography, it is a technique that is used to separate components in a mixture. So in paper chromatography, the paper is the stationary phase. So it stays there. And the water is the mobile phase. If you're using water or using alcohol. So this is the part that moves up in the stationary phase, and as the mobile phase moves up, it separates the components of the mixture. Now in gas chromatography, the mobile phase is an inert gas. For example, you can have helium. And the stationary phase is a liquid, which is also coated on a solid support on a thin capillary tube. So if you look at the column like this, in the column you're going to have the gas, let's say helium gas. This is the mobile phase, and as the gas moves through the column, it's going to separate the components. And in the column you have the stationary phase, which is the liquid coated on the long thin capillary tube that is inside an oven here. And as the components in the sample travels through the column here, so these are the components in the sample, as they travel through the column, it's going to separate according to their volatility and according to their solubility in both the mobile phase and the stationary phase. And at the end of the column, you will have a detector that will measure the amount of time between injection and the time that it is eluted. Eluted means that the time it took to move through the whole column and to move out into the detector. So that time is called the retention time. And depending on the retention time, it records a peak. And the area under the peak indicates the concentration of the component. So the more of that you will have, the higher the peak is going to be. And the peak is just the retention time. So the more soluble it is, the more it's going to have a small retention time. And the least solubility, so if it is least soluble, means it's going to travel slower. And when it travels slower, it's going to have a longer retention time. And at each retention time, you have one component, one compound. And that compound, if you couple a gas chromatogram with a mass spectrometry, so that compound can be further analyzed using a mass spectrometry, and it's going to give you a fragmentation pattern for that particular compound. So then it allows us to identify substances more accurately. So this is an example of a gas chromatogram where X is a sample, and under the area under the graph, this shows the intensity, the concentration of X, and the retention time will allow X to be identified because specific compounds have specific retention time, just like when we're doing paper chromatography. So different substances, different spots will produce different RF values. So in that case, for the gas chromatogram, we don't have a RF value, we have a retention time. So let's say we have a urine sample to be analyzed. This is the steps that has to be taken. First, the urine is injected in a gas liquid chromatography machine and carried by an inert gas through the heated liquid stationary phase. So the stationary phase, this is the part that is in the oven. And the inert gas, this is the mobile phase. And it is called a gas liquid chromatography machine because part of it, so this is the gas, this is the mobile phase, and the liquid is the stationary phase. So the stationary phase is coated on a solid support in a long, thin capillary tube. Normally, the longer the capillary tube, the better the separation. Then the second step, this process separates the components. As different components are eluted at the end of the column, they are passed into a mass spectrometer. So once we get this peak, so we know that this X is a compound, but what is it? Then we're going to take X and we're going to put it in a mass spectrometer. And then in the mass spectrometer, you're going to have the different peaks. And then the peaks produced by X will be compared to known samples. And then if it is a drug, then it's going to be identified. So then it is compared with spectra of known compounds. And then we are able to know their concentration in the urine sample. The next objective that we'll see is how alcohol can be detected using a breath analyzer. Let's now see breath alcohol testing devices. Now we know that injuries and death due to driving under the influence of drugs or alcoholic beverages is a serious problem. Now long ago, in order to detect alcohol in the blood, a blood test was required. However, by the time that you take the person to get a blood test done, the amount of alcohol has already decreased. So now we have techniques that allow the amount of alcohol in the blood to be determined very quickly. And this is called blood alcohol consumption or blood alcohol content rather, BAC. And this is done through a breathalyzer. And there's 3 types of equipment that can be used. We're going to see each one of them. So first one is a breathalyzer that detects alcohol by a redox reaction that produces a color change. So in a breathalyzer, so you have the breath that is blown through a tube containing crystals of potassium dichromate 6. So the dichromate 6 is reduced to Cr3+. And if we write the half equation, so we're going to start by writing the 2 species, and then we're going to balance the number of chromium. So I'm going to put a 2 here. I will balance the number of oxygen by putting H2O. And so 7. And I will balance the number of hydrogen by putting H+. So there's 14H+, and I will balance the charges by using electrons. So 6 electrons. So this is orange, and when it gets reduced, this changes to green. And if you look at oxidation of ethanol, ethanol is going to be oxidized. It's an alcohol. It's going to be oxidized to form ethanoic acid. So similarly, I will write the 2 species. I will balance the oxygen by adding H2O, and I will balance the hydrogens here by adding H+. So I'm adding 4H+, and I'm going to balance the charges by using electrons. So you can see that you have the oxidation of ethanol, and here you have the reduction of dichromate. And to write the overall equation, I'm going to multiply this by 2, and I'm going to multiply this by 3. So I change everything to 12 electrons. So the electrons will cancel out eventually. So these are the 2 equations written down after they have been multiplied, and you can see the electrons cancelling out. Water is going to cancel out, so 14 minus 3, so I'm going to be left with 11 H2O here, and the H plus will also cancel out, so 28 minus 12. And from this I can rewrite the combined equation. Right. So this is the same technique that we've used in topic 9, how to balance redox equations. Now the problem with portable breathalyzers is that they are not very accurate. A blood test is of course more reliable, so it just gives an idea of whether there's alcohol in the blood or not, but it's not very accurate and it cannot be used in court. An accurate concentration of alcohol concentration in the blood can be performed using IR, GC, or HPLC. GC is gas chromatography. HPLC is high performance liquid chromatography. Now, the alco sensor contains a fuel cell with 2 platinum electrodes. So you have an anode and a cathode, and you have a porous acid electrolyte material between the two. Now, when the suspect exhales into the fuel cell, if there is any ethanol in the blood, if has consumed any alcohol, the ethanol is going to undergo oxidation at the anode. Remember the cow rule, so oxidation at anode, and is also, so this is going to produce ethanoic acid, while oxygen is reduced at the cathode. So we'll have the oxidation of ethanol, just like we just wrote down previously. And then you have the equation for the reduction of oxygen to water. So I write the two species, and then I will balance the equation. So I balance the number of oxygen first, then I balance the hydrogen with H+, so 4, and then I balance the charges with electrons. So here I have my two half equations. From this I can write the overall equation. So the electrons will cancel out. Sorry, here you have 4 electrons. So electrons will cancel out, H+ will cancel out, and you end up with the overall equation. And the higher the concentration of the alcohol in the breath sample, the greater the electric current that is going to be produced by the fuel cell. Another equipment is called the intoximeter, which detects alcohol by IR. So an IR is going to detect the presence of alcohol by the absorption of infrared light at certain wavelengths. So in alcohol, in the ethanol, you have the CH and the CO bonds. And there's going to be 2 samples, one containing air and one containing the breath sample. If there is ethanol, alcohol in the breath, there's going to be a difference in the IR. So it's going to compare the 2 samples, the IR of the 2 samples. And the difference is going to be converted into concentration of ethanol in the breath. So this one is part of a question. So you have the acidified potassium dichromate. So this is the Redox breathalyzer here. And part 1 says, explain why the crystals turn green if there is alcohol in the breath, and give the 2 half equations and the overall equation. So the equations can be found here. So you can see the types of questions that you're going to get. And why it turns green, it is simply because the dichromate is reduced to form Cr3 plus ions, and this is green, right? And the second question, you have the fuel cell breathalyzer. And again, the half equations, you can include these 2 half equations and the overall equation here.